In late February 1908, in the damp sub-basement of the Institution of Civil Engineers on Great George Street in London, a junior archivist opened a misfiled shipping crate whose label had been washed blank by time and condensation. Inside, wrapped in brittle linen, lay a single cracked glass plate negative and a folded, water-scarred index card. The catalogue entry, typed decades later, calls it a conceptual study for a trans-Eurasian bridge, SAR 1876, never executed. Yet when the plate is printed, it isn't a drawing, it's a photograph, a stone and metal viaduct stretching across a wide river under a low fog. It spans too long for the recorded engineering of its year, a faint blur of carriages already crossing. The negative is stamped demolished 1878, meeting minutes from 1889 in the same archive, still debate whether to build it. The torn index card carries just two legible words: resonant piers. Radiators hum softly. Dust swims in the lantern beam. As the archivist turns off the light, the glass plate catches one last flicker, as if the river beneath that impossible bridge still reflects something moving. History remembers progress, but forgets what it replaced. By early May 1873, in the engineering pavilion of the Vienna Weltausstellung, visitors filed past a long table of bridge models under gaslight. A brass plaque in German and French explained that these were proposals for a future transcontinental rail corridor, linking Europe to Eastern territories. One model, catalogued as number 43B, showed a stone viaduct with metal ribs, its central span improbably wide, the deck thin as if weightless. Officially, the model was credited to an anonymous Russian delegation. The exhibition brochure lists it as experimental viaduct concept not approved, and yet, in a bound volume of photographs prepared for the emperor, the same bridge appears not as a model, but as a full-scale structure crossing a river labelled in faint ink, somewhere east of the Caspian. The photograph is dated August 1864. The brochure says the design was drawn up in 1872. One of those dates cannot be true. A marginal note in the precise hand of a Viennese curator reads, "This span does not calculate with current iron. Load tables suggest another material." Visitors to the pavilion in the warm, crowded May air would have heard only the murmur of voices and the occasional squeak of wooden floorboards. But technicians later reported a faint, steady vibration on the table under Model 43B, as if a distant train passed somewhere beneath the hall. The phenomenon is mentioned once, then never again. Today, a modern overpass outside Vienna follows a strangely similar curve, its pre-stressed concrete echoing the proportions of that forgotten model. To commuters, is just another bridge. The official record concludes the concept was never built. The photograph suggests someone, somewhere, crossed that span. On a dim January afternoon in 1883, in the reading room of the Institute of Civil Engineers in St. Petersburg, snow pressed thick against the high windows, muffling the city. An engineer named Pavel Kovalev leafed through a portfolio labelled Rejected Works, Foreign. Inside, he found a set of 6 blueprints for a bridge over the Neva. Official Russian records state that the permanent steel bridge at that crossing was inaugurated in 1890, yet these blueprints, stamped by a Parisian printing house in 1879, show a structure far beyond contemporary practice, a hybrid of arch and suspension, the deck carried by hollow stone pylons marked with spiral cross-sections and curious annotations at regular intervals. Node, harmonic, null. The approval minutes from 1885 call the design impractical, untested, foreign to our methods. But a water-stained postcard tucked between the sheets bears a hurried note from a French traveller dated 1891. Crossed the Neva today on a bridge of such lightness that the river itself seemed to carry it. No tremor, even as the tram passed. Locals say it has always been there. The Institute's inventory lists the drawings as unbuilt proposal. A pencil correction, later erased, had once altered that to retrofitted from earlier work. Only a faint indentation of the word remains. Kovalev is said to have tapped the tabletop absently as he studied the sheets. A colleague recalled that the ink bottles on the shelf rippled, though no cart passed in the street below. The temperature in the room was described as oddly even, despite drafty windows. Modern photographs of the current Geneva Bridge show standard steel trusses, replaced after wartime damage, yet satellite images reveal stone foundations beneath, with a spacing that matches the obsolete blueprints almost exactly. According to the 1883 catalogue, these sheets documented a structure that never left paper. The traveller's postcard and the foundations under the ice suggest otherwise. By late August 1893, visitors to the World's Columbian Exposition in Chicago wandered under strings of electric bulbs and plaster domes, the so-called White City glowing beside the lagoon. Tucked behind Machinery Hall, a raised walkway carried crowds over the service rail lines. Official maps call it a temporary viaduct, wood and plaster on iron. A surviving maintenance log, held in the Newbury Library, records routine inspections of that structure. Deck. No visible wear. Supports. No settlement. Note. No perceptible vibration under load, even during peak traffic. The viaduct appears in several lantern slides from the fair's closing months. In one, dated October 21st, the camera captures a twilight scene. People in hats and coats crossing the span, smoke from distant engines smearing the sky. Despite the caption, Timber Footbridge, the piers beneath the deck reflect light like polished stone, with fine joints too precise for rough carpentry. An internal fire brigade report contradicts the publicity. During a warehouse blaze on November film, the document notes, embers rained over the viaduct, surrounding decorative arches, constructed of staff. Plaster, mixed with fibre, caught fire and collapsed. The viaduct's surface blackened but did not ignite. A puzzled supervisor writes, "We were assured it was plaster." Yet the demolition records from spring 1894 list the bridge's material as salvaged metal, type unspecified. No weight, no destination, no buyer. Just a line drawn through the entry. On a breezy evening, one worker claimed he could hear a low, singing hum in the deck as crowds streamed over, a tone that remained constant whether 10 or 100 people walked. His foreman dismissed it. Wind in the wires. The site today holds a modern overpass and rail trench. Acoustic engineers testing traffic noise there in 2011 recorded an inexplicable, narrow frequency spike around 43 cycles per second. Precisely the pitch a 19th century tuning fork study once recommended to cancel lateral oscillation in bridge decks. In the ledger, that fairground viaduct was temporary, disposable, part of an illusion. In photographs and frequencies, it behaves like something built to last. If history is written by survivors, we might ask who edited its footbridges. On a chilly morning in March 1901, in the Municipal Archive of Pilson, clerks reorganising old engineering files found a slim ledger titled Demolition of Eastern Rail Viaduct, 1894. Outside, a damp mist clung to the red brick of the station. Inside, the air smelled of paper dust and coal smoke. According to printed timetables, a brick viaduct east of Pilson had been removed to facilitate line realignment 7 years earlier. The ledger dutifully lists the work, crews assigned, tools issued, days paid. But where one expects figures, cubic meters of rubble, tons of salvaged stone, the columns are blank. On the facing page, a pencil sketch shows 4 arches over a shallow cutting, each pier shaded with care. A note in Czech. No subsidence, no cracking under heavy freight, no resonant sway at marching cadence. A surviving photograph, found separately in a private album and dated, somewhat uncertainly, circa 1885, shows a bridge matching that sketch. Unusually slender piers with recessed panels, as if hollow, a metal rail hidden within stone. A military caption on the album's spine claims the structure was used for troop movements in 1898, 4 years after the supposed demolition. 2 dates, 1 bridge, one of them is wrong. In a brief memoir, a retired railway worker recalls being assigned to the removal as a young man. We waited 3 weeks by the embankment, but no explosives came, no engineer. Then the order arrived. Record it as done. The bridge remained. We called it the Ghost Viaduct. During those idle weeks, he notes, the men passed time listening to the wind under the arches. He writes of a steady tone, lower than a bell, but clear, that did not change when trains passed overhead. Today, satellite imagery of the spot reveals only a shallow depression and a curved stand of trees, following the line of a vanished embankment. Yet ground-penetrating surveys done for a nearby road project detected dense regular masses below, like piers, the report says, but deeper and narrower than expected. The archive insists the viaduct was removed. The earth insists something remains. In early November 1889, heavy rain fell over Lyon, France, turning streets slick and amplifying the sound of carriage wheels on stone. In a vaulted office near the Saône, the city's chief engineer reviewed inspection notes for the Pont des Arts et Métiers, a modest masonry bridge widened earlier that year. Official paperwork describes a standard widening, new sidewalks added, railing replaced, the usual stiffening to accommodate trams. Yet the original 1862 construction log, preserved in the same box, lists dimensions and materials that don't quite match what the widening crews reported. Piers documented as solid ashlar stone were found to be layered with unknown composite, ringing dully under the hammer, resisting the drill. Among the widening reports, one foreman's note stands out. When troops march in formation, we observe no rhythmic amplification of movement. The deck refuses to enter cadence. Orders given to break step proved unnecessary. Engineers of the era feared resonance. Soldiers were routinely instructed not to march in step across bridges. Yet here, the phenomenon seemed reversed. The structure absorbed rhythm, cancelling it. A margin calculation attempts to model the effect using pendulums and mass, then trails off. The same folder contains a sepia photograph of the bridge taken from the quay in 1874. Along the waterline, faint markings appear on the stone piers, regular vertical slots, later infilled. The caption, added decades after, reads simply, "Before modernization." On a smudged scrap of paper clipped to the file, an anonymous hand has written, "Piers behave like tuned bells, but bells of silence." Outside, that rainy night, gaslights reflected on the river's surface. Witnesses described a low constant hum where the arches met the water, distinct from the rush of current. Modern structural retrofits added steel and concrete to the bridge in the 20th century. Noise and vibration studies conducted before the work, now digitized, record a sharp attenuation of certain frequencies around 40-45 Hz. Today, electronic equipment used on the bridge, survey drones, phone antennas, occasionally experience interference. Officially, these are quirks of old masonry and urban electromagnetism. To those who read the old notes, they look more like traces of a material logic no longer taught. On a hot June day in 1897, in the planning office of the Transcaucasian Railway in Tiflis, now Tbilisi, ceiling fans stirred dust over drafting tables. Mountains shimmered in the distance. A visiting auditor from St. Petersburg later described an unusual quiet in the bridge design department. In a surviving group photograph from that year, 5 engineers pose stiffly around a table strewn with blueprints. One man's face, at the right edge, has been carefully scratched away, leaving a white oval. The caption on the back lists 4 names. The 5th is missing. In the plan drawer, among standard truss designs, there survives a single cross-section, drawing labelled only Bridge 17, Aras River Crossing. The date title block reads Project 1886, revised 1896. 2 dates, no explanation. Unlike the others, this drawing shows piers with intricate internal cavities, spiral channels and lens chambers, annotated with small symbols, waves, arrows, and numbers corresponding to frequencies in cycles per second. A faint note in Russian near the margin says, appears to be filled with composite mixture, non-metallic. Resonant tuning supervised by name illegible. Important, do not document origin of mixture. According to official construction reports, the Aras River Bridge was built according to standard imperial specifications. Its designer listed simply as technical staff. Tiflis. Freight logs from the 1890s praise its stability during floods and earthquakes. A clerk's private diary housed in the Georgian National Archives recalls overhearing a conversation. The man from the east insists we follow his measures exactly. He says if we change the thickness by even a finger, the river will find the weakness. When asked where he learned this, he only replied, from older bridges, now gone. We were told not to write his name. Standing by the riverbank today, the modern replacement bridge shows standard reinforced concrete, but low water reveals older stone foundations beside it, unused yet intact, bearing tool marks, unlike neighbouring structures. Local children, playing on them, report that when trucks pass the new bridge, they feel a faint vibration in the old stones, like a heartbeat, even though no load rests upon them. In the cleaned-up digital archive, the unidentified engineer remains faceless, his signature erased. The physics he sketched into those spiral piers continues to hum beneath a different flag. By October 1934, autumn fog pooled in the courtyards of Moscow's People's Commissariat for Transport. Inside, beneath the newly installed fluorescent lights, a committee convened to rationalize the empire's bridges. The Soviet state, inheriting a patchwork of Tsarist and foreign infrastructure, demanded uniformity. The decree drafted that week, now preserved in crisp typescript, orders the review, redesign or replacement of all pre-revolutionary bridges not meeting new standardized calculations. It references an earlier, lost document, Inventory of Anomalous Load Capacities in Imperial Stone Bridges, 1890. The inventory itself is not found in any catalogue. Only this echo remains. Attached to the decree is a microfilm reel, mislabeled Agricultural Statistics, discovered decades later in a cardboard box. When projected, it reveals densely typed tables, span lengths, materials, estimated safe loads. Some numbers are conventional. Others defy expectation. Stone viaducts rated for axle weights typical of mid-20th century locomotives, long before such engines existed. In the margins of one table, a faint handwritten note in pre-revolutionary orthography reads, "Values confirmed by experiment. Unknown factor in pier composition, possibly conductive." A second hand, later, stamps over it. Outdated. Do not use. A surviving memo from a regional engineer in Kazan, dated January 1892, but filed with the 1934 reel, describes testing an older bridge. We loaded the span beyond calculated failure. The stone did not crack. The deck did not sink. Instead, we observed a low vibration throughout the structure, uniform and calming, as if the bridge redistributed stress like water-seeking level. The test date, 1892, predates the supposed issue of the inventory by 2 years. Yet the memo is indexed under 1894. Two timelines cross in the same folder, imperfectly aligned. Outside, in the coal fog, trains continued to cross hybrids of old stone and new steel. Inside, the committee signed off on replacement plans. Blueprint annotations from the late 1930s show many of those overperforming stone arches, encased in concrete or dismantled and rebuilt with standardized beams. Today, along certain Siberian lines, satellite images still reveal lonely stone piers standing beside modern girder bridges, half buried in silt. Railway manuals dismiss them as obsolete supports. The standardization decree simplified calculations. It also quietly buried a century of anomalous performance under the phrase non-compliant design. If history is written by survivors, standardization writes in a single hand. In late September 1864, in a foundry yard on the outskirts of Prague. Fog rolled low over stacks of stone blocks and iron castings. The records call it the Smyshov Bridge Workshop, subcontracted to supply components for rail viaducts across the Austro-Hungarian Empire. A surviving workshop notebook, stained with oil and lime, describes an unusual commission. Client request hollow stone members, moss-free, with internal channels according to the foreign pattern. The date atop the page reads 1860, but an ink blot in the corner obscures a hastily written 59, as if the year had been corrected. Sketches on the facing page show cross-sections of pier blocks, not solid rectangles, but nested spirals, cavities winding inward like snail shells. Small annotations mark specific dimensions alongside single letters A, E, G, C, as if referencing musical notes. Beside them, a word, Stimmung, tuning. One worker's letter, home, preserved by chance in a family trunk, mentions an experiment after hours. We struck one of the blocks with a hammer to hear its ring. It sounded not like stone, but like a deep bell, the tone constant no matter where we hit it. When we placed several together, the sound became softer, almost a feeling rather than a noise, and the lamps on the wall flickered in response. Official orders list the blocks as destined for a minor viaduct near Brno. No bridge in that region today matches their described dimensions. A viaduct built there in 1870 uses conventional masonry according to modern surveys. Yet fragments recovered from a collapsed retaining wall near the old line in 2002 show traces of an unusual cement, richer in silica and metallic inclusions than typical 19th century mixes. When tested in a lab, small samples produced a measurable voltage when subjected to mechanical stress, a modest piezoelectric effect, unexpected in common stone. The workshop notebook contains a single tantalizing phrase written in a different ink. As in the Eastern drawings, arches that calm the earth's shaking, piers that hum instead of crack. No source is cited. Bridge manuals of the period discuss resonance only as a danger to be avoided. These stones appear designed to engage it. Tuned cavities turning stress into vibration, vibration into something else. Today, high-speed rail viaducts use tuned mass dampers and sophisticated materials to counter oscillation. In their internal shapes, some echo those forgotten spirals from 1864. The language has changed, the principles quietly repeat. On a wind-scoured day in April 1872, a British surveyor named Henry Lawson closed his field journal in frustration near the Tartaria River in Central Asia. The air shimmered with heat, dust blew in thin veils over the reeds. His official task, recorded in the Indian Office archives, was to map potential crossings along a route sketched in London but never built. In his journals, however, he described stumbling upon a bridge that should not have been there. London's maps for that year show only a ferry. Russian military charts mark ford, no crossing. Yet Lawson writes, "We came upon a stone bridge of 4 spans, arches shallow and wide, the deck seemingly without sag. No road leads to it from our side, only a worn track. The locals say it was there before their fathers, yet it looks younger than the mosques." He notes an odd detail. The underside of the arches carried not rough stone, but smooth, jointless surfaces. Striking them with a rifle butt produced a low, almost bodily hum, not pleasant, yet not loud. The date at the top of his entry reads 1872. A later cataloguer, copying the pages, added a parenthetical. Possibly 1874. The uncertainty persists in the metadata. Lawson includes a rough sketch, piers slightly skewed relative to the river, as if aligned with some other invisible grid. In the margin, he draws a compass with arrows, labelling N one way and flow another. He writes, "Needle behaves oddly on deck. Points between north and east. Could not establish true bearing while standing on the bridge. Official correspondence back to London omits the bridge entirely, describing only difficult fordage and recommending a future iron crossing. The omission is striking. In the late 20th century, a Soviet hydrological survey references remains of an old masonry bridge, partially submerged, at coordinates matching Lawson's hand-drawn map. The report complains of interference during magnetometer readings near the site and advises avoiding the area for calibration tests. Satellite images today show faint linear scars leading to the river, hints of abutments in the shallows, and a modern concrete span built a few kilometres downstream. Nothing in standard bridge histories mentions a humming stone span on the Tartaria. Yet a Victorian surveyor's sketch, a wandering compass, and a modern instrument's misbehaviour suggest that someone, long before railways, understood how to anchor arches not just to the ground, but to fields we no longer measure. In a cluttered physics laboratory in Berlin in November 1890, coal stoves ticked as they cooled, and early electrical apparatus sat half disassembled on wooden benches. Among papers on induction coils and cathode rays, a slim folder in Professor Heinrich Krüger's collection bears the nondescript title Stone Samples MISC. The folder contains a handful of test notes on fragments sent from bridge works in Bohemia. The covering letter, lost, is referenced only by number. The date on the first test sheet reads 1889, while a library stamp on the folder's cover adds received 1893. Two dates, 3 years apart, for the same brittle pages. Krüger's assistant subjected the stone fragments to repeated mechanical loading using a small press, while connecting them to a galvanometer. The notes record a weak but consistent current whenever pressure changed. Response approximately proportional to applied stress, waveform similar to that seen in certain quartz. A sketch of the signal's oscillation repeats several times, annotated with frequencies in the range of 40-45 Hz. In the margin, the assistant has scrawled, Bruckenstein behaves as if it were a battery when struck. Could such material be used to sense loads? Or more? On a separate page, half crumpled, Krüger himself has written in a tighter hand, if piers composed of such material were tuned to specific frequencies, they might dissipate dangerous oscillations, or convert them. Imagine a bridge that feeds on its own resonance. No subsequent publications under his name mention this line of inquiry. Instead, Krüger's known work shifts fully to electromagnetic waves in air, joining the race that would lead toward wireless telegraphy. The stone fragments, recently rediscovered in a museum drawer, were retested in the early 2000s with modern instruments. The piezoelectric effect is real, though modest. When vibrated at about 43 Hz, they produce their strongest response. The composition, a dense composite of crushed stone and an unknown binder, does not match standard 19th century mortars. According to bridge treatises of the era, control of resonance relied on mass and stiffness, not on materials that could feel vibration electrically. Yet these anonymous fragments, marrying stone and subtle currents, embody a hybrid logic: mechanical, acoustic, electromagnetic. Today, engineers embed sensors in concrete and steel to monitor bridge health, converting stress into data. In Krüger's dust-covered lab notes, we glimpse an earlier, stranger version of the same idea, one that never quite entered the textbooks, and whose origin had already been forgotten by the time those samples reached his bench. On a bright March morning in 1905, in a lecture hall at Tokyo Imperial University, Professor Tanaka Kiyoshi addressed a small audience of engineering students. The cherry trees outside had not yet bloomed, the air inside was still and cool. On the lectern lay a recently imported German text on bridge design, its margins already filled with careful Japanese notes. The official subject of Tanaka's lecture, according to the university timetable, was modern European methods in iron bridges. Yet among his surviving papers is a single sheet, never published, in which he sketches an arch form not in the German book. The curve is flattened, elliptical, its intrados segmented by points labelled with small kanji for tone and silence. In the corner of the sheet, he has copied a fragment of a European drawing, a pier cross-section with an internal cavity, spiral in shape. The source is unidentified. Beside it he writes, Western stone, tuned, remember story from Lyon, bridge that will not march. The date on his sheet reads Meiji 38, 1905. A later archivist's penciled notation, misreading the characters, catalogues it under 1908. Tanaka's marginalia gesture towards something older than the steel latticework his students admired. There are whispers of continental bridges whose tremors vanish, whose stones drink sound. Are these myths or remnants of a craft now broken? Decades later, Japan would build some of the world's most advanced rail viaducts for its Shinkansen lines. Slender concrete structures with carefully tuned stiffness and mass to avoid resonance. Their piers aligned not just with geography, but with seismic constraints. Early internal design reports from the 1960s occasionally compare certain test geometries to old European arches, noting how particular curves diffuse vibration like ripples in water. In a 1971 technical memo, a young engineer references, almost as an aside, Tanaka Sensei's discarded notes on harmonic spans, found in a library box. The memo's photocopy is faint, the original notes are missing. Standing beneath a Shinkansen viaduct today, one can feel a subtle, even trembling when the train passes overhead, a carefully managed spectrum of frequencies. Microphones placed under some spans record a narrow band hum amid the roar, a modern engineered song. The line from hollow stone piers in Europe to pre-stressed concrete in Japan is neither straight nor documented. Yet in curves, frequencies, and the quiet ambition to make bridges that do not shake themselves apart, an echo persists. If history forgets the names of those who first tuned stone to sound, their intentions may still travel, embedded in rebar and code. On a grey February afternoon in 1924, representatives of several nations gathered in a modest conference room in Geneva under the banner of the League of Nations. Outside, the lake lay flat and dull. Inside, the room smelled faintly of tobacco and damp wool. The committee's task was pedestrian, to discuss international standards for obsolete infrastructure management. Among the background documents, now bound together in a single volume, is a report from a Swiss engineer named Müller, summarizing responses to a questionnaire circulated across Europe. Many countries reported aging bridges deemed overbuilt by contemporary standards, their replacement motivated less by necessity than by economic logic. One line in Müller's summary is underlined in pencil. Several states note pre-war stone bridges that show higher load tolerance than calculated, often of unclear origin. He mentions in particular a response from an unnamed Eastern delegation describing archaic viaducts whose piers seem impervious to fatigue, noting that their demolition could supply reusable stone or composite material of unusual density. No technical appendix is attached. A draft resolution proposes cataloguing such structures before removal. The handwritten date on the draft is 1924. The final printed resolution, however, dated 1925, omits the catalogue entirely, referring only to the rationalization of networks and removal of redundant crossings. Somewhere between draft and print, the inventory vanished. In the margin of Müller's personal copy, a frustrated note: "We are erasing more than stone. No funds to record origins, no interest in anomalous performance, only scrap value. Later, historians will see only numbers, not the bridges that bore them." National archives from the following decade show a steady uptick in demolition reports. Many older bridges are described tersely, removed due to modernization, with no mention of original builder, material peculiarities, or unusual resilience. Shipment records for salvaged stone and metal are often incomplete, destination fields left blank. One French demolition log from 1932 lists a rural viaduct whose piers, upon being broken up, revealed hollow cores lined with smooth material that dulled tools and rang like glass when struck. The supervising engineer notes, composition unknown, samples sent to Paris. No follow-up exists in the file. Today, modern motorways cross valleys where such viaducts once stood, their alignments slightly shifted. In some cases, Grassy mounds beside the new embankments mark where old piers were buried, rather than fully removed. Too difficult to break, not worth the cost. Official histories of the League of Nations make no mention of anomalous bridges. The Geneva minutes record discussions of tariffs, borders, and treaties, not resonant stone. Yet in Muller's forgotten draft, in his underlined phrases and marginal pleas, we glimpse an engineer aware that something more than infrastructure was being quietly, efficiently, and bureaucratically erased. On a cold evening in January 2019, an urban explorer named Eleanor stood beneath a 19th century stone rail viaduct on the outskirts of a Central European city, her breath visible in the air. The bridge above carried commuter trains. The official plaque nearby dated its construction to 1882, with a major renovation in 1954. Floodlights cast harsh angles on soot-stained arches. Eleanor's stated project, in a now deleted video description, was simple: to record the voices of old infrastructure, the creaks, echoes, and hums of forgotten spaces. Using a contact microphone and a portable recorder, she fixed the sensor to the base of one pier, its cable snaking to the device in her gloved hand. As a train passed overhead, the recording captured the expected roar and rumble. But when she filtered out the obvious noise at home, a narrow band remained, a low, steady tone around 43 Hz, present even between trains, faint but persistent. The stone under her fingers that night had felt oddly warm compared to the air, a detail she mentions once in a comment reply before her channel went dormant. Local municipal records describe the viaduct's original construction in typical terms: cut stone, lime mortar, later concrete reinforcement. A single line, faded in an 1881 engineer's notebook, adds, "Piers filled according to imported specification, material not supplied by our usual vendors." The supplier's name is smudged beyond recovery. A 1950s restoration report notes difficulty drilling into the lower sections of the piers, describing the core material as denser than surrounding stone, uniform, ringing under bit. The recommendation: avoid disturbing core where possible, anchor reinforcements in upper masonry instead. After Eleanor posted a short clip of the bridge's hum online, some viewers complained of headaches when listening with headphones. Automated content systems later flagged the video's audio as problematic frequency content, a generic label often applied to recordings containing tones that interfere with compression algorithms. The video was eventually removed. An archived mirror survives in a corner of the internet, its view count frozen. Trains still cross that viaduct each day. Commuters scroll through their phones, unaware that the stone beneath them sings in a key once penciled in margins beside sketches of hollow piers and spiral cores. Standing under such bridges, if you press your palm to the cold block and listen, not with ears, but with the sense that feels the thrum of blood, you may catch a hint of that persistent tone, part mechanical, part something else. According to official histories, Tartaria is a cartographic convenience, a name for lands once poorly known. Its impossible bridges, if they ever existed, occupy no line in accredited textbooks. Yet in misdated plans, erased names, humming piers, and fragments of composite stone that behave like forgotten instruments, a pattern flickers, too consistent to dismiss, too incomplete to confirm. The reel runs out on the image of a train crossing a soot-dark arch at dusk, its windows lit, its passengers anonymous. The camera lingers not on the moving carriages, but on the pier below, where a contact microphone once clung, and where dust still vibrates imperceptibly to a frequency no longer measured, but not yet entirely silent.